Certainty was murdered sometime around the year 1900, and almost nobody noticed at first. For a very long time, humans believed they lived inside a machine. A grand, ticking, predictable machine. This was Newton's universe. Drop an apple, and it falls. Fire a cannonball, and you can calculate exactly where it lands, down to the inch. Before it even leaves the barrel, every object, every force, every motion obeyed rules so tidy that scientists began to whisper a dangerous sentence to themselves. They said, "We have basically figured it all out." This is, historically speaking, always the exact moment right before everything falls apart. Because physics, at the end of the 1800s, had one small problem. A problem so embarrassing that physicists initially just called it the ultraviolet catastrophe, which is a name that sounds like a Bond villain, but is actually just a math error so severe it predicted that a warm object, like, say, a fireplace or a piece of toast, should emit an infinite amount of energy. Not a lot of energy. Infinite energy. Now, if your equations tell you that a candle should output more energy than exists in the entire universe, you have two choices. You can either assume the universe is broken, or you can assume your equations are broken. Most scientists, understandably, leaned toward blaming the universe. It took one stubborn, meticulous German physicist named Max Planck to consider the second option. Planck was not trying to overthrow physics. He liked physics exactly the way it was. He was, by most accounts, a deeply conservative thinker who wanted nothing more than to patch this one annoying gap in the equations and go back to a nice, orderly universe. So in the year 1900, somewhat reluctantly, he proposed a strange fix. What if energy wasn't smooth? What if energy, instead of flowing like water from a tap, actually came out in tiny, indivisible packets? He called these packets quanta, and honestly, he treated the idea less like a discovery and more like a mathematical trick he didn't fully believe in. He fixed the equation. The infinite energy problem vanished. And Planck went home, presumably relieved, having no idea that he had just detonated an intellectual bomb that would take apart the entire foundation of physics. Because 5 years later, in 1905, a young patent clerk in Switzerland picked up Planck's strange little idea and did something far more radical with it. His name, you may have heard of him, was Albert Einstein. Einstein looked at light. For centuries, physicists had firmly established that light was a wave, smooth and continuous, like ripples spreading across a pond. This was settled science. It was, in fact, one of the great triumphs of the 1800s. And Einstein, in one of the boldest moves in scientific history, looked at all that settled certainty and said, essentially, what if it's also a bunch of tiny particles? Not instead of a wave. In addition to being a wave, this is the point where, if you are listening carefully, your brain should feel a small uncomfortable itch. Because a wave and a particle are not the same kind of thing. A wave is spread out, a disturbance moving through space. A particle is a distinct located object, like a marble. Asking whether light is a wave or a particle is a little like asking whether a song is a sound or a memory. The honest answer, infuriatingly, turns out to be both, depending entirely on how you choose to look at it. Einstein called these particles of light photons, and he used this idea to explain something called the photoelectric effect, a phenomenon where shining light on certain metals kicks electrons loose, but only if the light is the right color, no matter how bright you make it. Wave theory couldn't explain this. Particle theory could. And for that insight, not for relativity, which is what most people assume, Einstein eventually won his Nobel Prize. So now we have two cracks in the machine. Blackbody radiation, patched by Planck's quanta dot. The photoelectric effect, explained by Einstein's photons. Two separate problems, solved by the exact same strange idea that energy, and possibly reality itself, is not smooth. It is grainy. It comes in indivisible little chunks. Here is where the analogy becomes useful. So let's slow down and really sit inside it. Imagine you have lived your entire life beside a river. To you, this river is a smooth, continuous thing. Water flows, it swirls, it splashes, and at no point does it look like it's made of separate, distinct pieces. It behaves like one unbroken substance. Then, one day, someone hands you an impossibly powerful magnifying glass, and you look closer than any human has ever looked before. And you discover, to your considerable shock, that the river is not smooth at all. It is made of individual, indivisible droplets. You can have one droplet. You can have two droplets. You cannot, under any circumstances, have 1.5 droplets. The smoothness you experienced your entire life was never real. It was an illusion, created by billions of discrete little events happening so fast and so small that your eyes simply blurred them together into something that looked continuous. This is exactly what Planck and Einstein discovered about energy, and eventually, about the entire universe. Reality looks smooth to us the same way that river looks smooth. But zoom in far enough, and the smoothness dissolves into grains, discrete, indivisible packets. Quanta. The continuous world you touch, see, and stub your toe on every single day is underneath, made of tiny discontinuous jumps, blurred together by your senses into something that feels seamless. This single idea, that nature is fundamentally grainy rather than smooth, is really the seed of everything that follows in the story of quantum physics. Every strange, mind-bending idea still to come, superposition, entanglement, uncertainty, all of it grows out of this one uncomfortable realization. The universe does not do things gradually at its deepest level. It does things in steps. Sudden, discrete, indivisible steps. But the story of the classical world's collapse wasn't finished yet. There was still the small matter of the atom itself. At the time, physicists imagined atoms a bit like miniature solar systems. A dense nucleus sitting in the center, like a sun, with electrons swirling around it in smooth, continuous orbits like planets. It was an elegant picture. It was also, according to the physics of the day, completely impossible. Here is the embarrassing detail nobody likes to mention. Classical physics insisted that an electron orbiting a nucleus should constantly radiate energy, spiraling inward in a fraction of a second, crashing into the nucleus like a doomed satellite falling out of the sky. According to the old rules, every atom in the universe should have collapsed in an instant. Which is obviously a problem, since atoms are famously still here, and so for that matter are we. It took a Danish physicist named Niels Bohr to solve this using the same trick Planck had already discovered. What if electrons couldn't orbit at just any distance? What if, instead, they could only exist at specific, fixed, quantized energy levels, like rungs on a ladder, with absolutely nothing allowed in between? An electron could jump from one rung to another instantly, but it could never, under any circumstances, hover somewhere in the middle. This was strange. This was also remarkably correct. Bohr's quantized atom explained things the old model never could, and it confirmed once again that the universe simply refuses to behave smoothly once you look closely enough. So by the end of this chapter, the machine that Newton built, the tidy, predictable, clockwork universe that had reigned for over 2 centuries, was quietly, irreversibly broken. Not because scientists had made a mistake, but because reality itself had never actually been smooth. It only looked that way. The same way the river only looked smooth. The same way a movie only looks like continuous motion when it's really just individual, still frames flashing past faster than your eye can catch them. Certainty didn't die because someone killed it on purpose. It died because someone finally looked closely enough to see what was always hiding underneath. And once you see the grain in the river, you can never quite convince yourself the water is smooth again. That unsettling, quiet realization is where our story truly begins. There is one experiment in the history of science that physicists themselves describe as impossible to fully understand. Not difficult, impossible. And yet you can build it on a tabletop. It's called the double-slit experiment, and it's where our story stops being merely strange and starts becoming genuinely unsettling. Let's begin gently with something familiar. Waves. If you've ever watched 2 stones dropped into a still pond at the same time, you've seen ripples spread outward from each point, and where those ripples cross, something interesting happens. Where 2 peaks meet, the water rises higher. Where a peak meets a trough, they cancel out, and the water goes flat. This crisscrossing pattern is called interference, and it is the unmistakable signature of a wave. Waves interfere. Solid objects do not. You will never see 2 thrown baseballs pass through each other and cancel out mid-air. Now, take a barrier with 2 narrow slits cut into it, and shine light through it onto a screen behind. Light, as we established in the last chapter, behaves like a wave. And sure enough, The light passing through both slits spreads out, overlaps, and produces exactly that interference pattern on the screen. A series of bright and dark bands, alternating like some cosmic zebra print. Nothing strange yet. Waves interfere. Light is a wave. Case closed. Except physicists, being constitutionally incapable of leaving anything alone, decided to ask a further question. What happens if, instead of a steady beam of light, you fire electrons, one at a time? Not a flood. A trickle. One single electron, then a pause, then another. Each electron is, by every definition we have, a particle. A discrete little chunk of matter, not a spread-out wave. So logically, each electron should go through one slit or the other, like a marble dropped through one of two holes, and land on the screen as a single dot directly behind whichever slit it passed through. Fire enough electrons, and you should end up with two clean clusters of dots, one behind each slit. Simple. Predictable. Exactly what you'd expect from a solid, sensible particle. That is not what happens. Each individual electron does indeed land as a single, sharp dot on the screen. Precisely the behavior you'd expect from a particle. But here's the part that has quietly disturbed every physicist who has ever performed this experiment. If you let thousands of these individual electrons accumulate, one dot at a time, patiently building up over minutes or hours, the dots do not form two clusters. They slowly assemble into the exact same banded interference pattern you saw with waves of light. Sit with that for a moment, because it deserves more than a passing glance. Each electron arrives alone. Each electron leaves a single dot, like a lonely period at the end of an unfinished sentence. And yet, collectively, across time, those isolated dots conspire to recreate a wave pattern. It is as if each electron, entirely by itself, somehow passed through both slits simultaneously, interfered with itself on the other side, and only then decided where to land. A single electron, behaving like two. Naturally, physicists did what physicists always do when reality misbehaves. They decided to watch more closely. They placed a tiny detector right at the slits, a sort of quantum doorbell whose only job was to notice which slit each electron actually passed through. And the moment they did this, the universe blinked. The interference pattern vanished. Completely. The moment you observe which slit the electron travels through, it stops behaving like a spread-out wave and starts behaving like an ordinary sensible particle, going cleanly through one slit or the other, forming two simple clusters on the screen, exactly like the marble everyone expected in the first place. Nothing about the electron's physical journey changed. No wall was moved. No slit was widened. The only thing that changed was that somebody looked. And looking, somehow, altered the outcome. This is not a flaw in the measuring equipment. Scientists have run this experiment for over a century, refining it, questioning it, trying desperately to find some hidden mechanical explanation, some sneaky vibration or stray photon bumping the electron off course. There isn't one. The act of observation itself appears to force the electron to commit to being one thing or the other. Unobserved, it exists as a haze of possibility, behaving like a wave. Observed, it collapses into a single, definite location, behaving like a particle. Let's bring in the analogy, because this is the moment it earns its keep. Picture a particular person, we'll call him a rather ordinary fellow who has a peculiar quality. Whenever nobody is watching him, he stops being one solid person. He dissolves, quite literally, into fog, a thin, drifting mist of himself. And in this foggy state, he doesn't walk through one doorway of a house. He drifts through both doorways at once, his fog self-splitting and spreading and reconverging on the other side, the two streams of mist crossing and interfering with each other, creating swirling patterns in the air. But the instant you set up a camera to catch him in the act, something remarkable happens. He is no longer fog. He snaps instantly into a single, solid, entirely ordinary man, walking calmly through exactly one doorway, as though had never considered doing anything else. And the swirling interference pattern, the strange fog trails on the other side, simply disappear, as if they were never there. The unsettling implication is not merely that watching him reveals which doorway he used. That watching him seems to decide which doorway he used. Before you looked, there was no fixed answer. He wasn't secretly walking through the left doorway, while cleverly disguising himself as fog to fool you. He genuinely existed as both possibilities at once, a real, physical haze of potential, right up until the moment observation forced a decision. This is the strange heart of wave-particle duality. It is tempting and comforting to imagine that electrons are secretly one thing, either a wave or a particle, and that we've simply been too clumsy to catch them in their true form. But nature offers no such comfort. An electron isn't a wave wearing a particle costume, or a particle occasionally pretending to spread out. It is something genuinely in between, something our language and our intuition, both built entirely by watching baseballs and rivers and doorways, were simply never designed to describe. What it is depends, quite literally, on how you choose to interact with it. Don't look and it behaves as a spread of possibilities, rippling and overlapping like a wave. Look, and it snaps into a single definite outcome, landing like a particle. The observer is not a passive bystander quietly recording a pre-existing reality. The observer is, in some deeply strange sense, a participant in deciding what that reality turns out to be. And once this idea settles in properly, once you really let it sit, a much larger and stranger question begins to surface quietly at the edge of the mind. If observation can determine outcomes at the level of a single electron, then what, exactly, is an observation? Does it require a human being? A camera? Consciousness itself? Or is the entire universe simply a vast, ongoing negotiation between possibility and certainty, endlessly resolving itself every single time something, anything at all, happens to be looking? That question, patient listener, is the doorway to everything still ahead. There is a word in quantum physics that sounds gentle, almost poetic, but hides one of the strangest ideas the human mind has ever tried to accept. That word is superposition, and it means, quite simply, that a thing can be everything it's allowed to be, all at once, until something forces it to choose. Let's start with a question that sounds almost too simple to matter. Where is an electron? In the ordinary world, this question has an ordinary answer. You point. You say, there, that's where it is. Coffee cup sitting on a table has a location. It is not smeared across the room. It is not simultaneously on the table and in the sink. It simply is where it is, whether you're looking at it or not. Quantum particles refuse this courtesy entirely. Before you measure an electron's position, it does not have one single location that you merely fail to know about. It exists instead in something physicists call a wave function, and this is worth sitting with, because it is easy to misunderstand. The wave function is not a physical wave rippling through space, like a wave on the ocean. It's better described as a wave of probability. A mathematical description that says, essentially, here are all the places this electron could be found, and here's exactly how likely each one is. This is not a metaphor for our ignorance. It is not physicists shrugging and saying, we don't know where it is, so we'll just guess with percentages. The electron before measurement genuinely does not possess a single definite location. It exists as a blur, a smeared overlap of every possible position it could occupy, each one weighted by probability, all of them equally real, all of them equally true, right up until the instant someone measures it. This connects directly back to that double-slit experiment we sat with in the last chapter. Remember the electron that seemed to pass through both slits at once, interfering with itself before landing as a single dot. That wasn't some clever trick of light or some illusion of measurement. That was superposition, made visible. The electron, unmeasured, existed as a wave function spread across both slits simultaneously. It wasn't hiding a secret choice of which slit to use. It hadn't made a choice at all. The interference pattern was the literal physical signature of a particle being, quite genuinely, in two places at once. Now here is a lovely piece of evidence that superposition isn't limited to electrons slipping through slits. In the 1920s, two physicists named Otto Stern and Walther Gerlach ran a rather elegant experiment involving silver atoms. Silver atoms, it turns out, carry a property called spin, which behaves, for our purposes, a bit like a tiny internal compass needle. Stern and Gerlach fired a stream of these atoms through a carefully shaped magnetic field, expecting, quite reasonably, that if these atoms really did have compass-like spins pointing in random directions, they should land smeared in a continuous band on the detector behind, since a compass needle can point anywhere between straight up and straight down. That is not what they found. Instead, the silver atoms split cleanly into exactly two groups. Some atoms landed deflected one way, labeled spin up. Others landed deflected the opposite way, labeled spin down. Nothing landed in between. No atom was ever caught pointing sideways or diagonally or anywhere else on the compass. Spin, it turned out, is quantized, restricted to just two possible outcomes, with absolutely nothing allowed in the middle. And before measurement, an atom doesn't secretly possess one of these two spins waiting to be revealed. It exists in a superposition of both, up and down simultaneously, until the magnetic field forces it to commit to one. This is admittedly a peculiar thing for the universe to be doing. So let's reach for an analogy, because superposition genuinely benefits from a mental image, provided we handle that image carefully. Picture a coin, flipped into the air, spinning. While it's spinning, tumbling end over end, it is not showing heads, and it is not showing tails. In some loose, everyday sense, you might say it's both. A blur of two possibilities, undecided until it lands and you glance down to see which face is up. Now here is where most people, quite reasonably, get the analogy slightly wrong, and where the real strangeness of quantum physics lives. Your coin, spinning in the air, always secretly has a definite face at any given instant. If you had a camera fast enough, absurdly fast, capable of freezing time itself, you could snap a photograph mid-spin and see, with total clarity, that the coin was showing heads at that exact frozen moment, whether anyone was watching or not. The coin's ambiguity is entirely a limitation of your eyesight, not a property of the coin. It was never actually undetermined. You just weren't fast enough to catch it. The quantum particle offers no such loophole. There is no faster camera. There is no hidden frozen instant where the electron secretly does have a definite position, or the silver atom secretly does have a definite spin, patiently waiting for a sufficiently clever observer to catch it in the act. The superposition is not a speed problem. It is not a resolution problem. The property itself simply does not exist yet, in any meaningful sense, until the act of measurement forces the universe to settle on an answer. It's a bit like saying the coin doesn't merely conceal its face while spinning. It's more accurate, however uncomfortable, to say that the coin has no face at all until the exact instant it lands. Heads and tails are not two hidden truths waiting patiently inside the spinning coin for you to discover. They are two potential futures, both equally real, both equally available, and the landing itself is not a revelation. It is a decision made by reality in real time with no advanced planning whatsoever. This is the part where most people's intuition simply refuses to cooperate, and honestly, that's a perfectly reasonable reaction. Our entire evolutionary history prepared us to track solid objects with definite locations, because our ancestors needed to know precisely where the leopard was, not a probability distribution of where the leopard might be smeared across the savannah. Human brains were never built for superposition. We were built to dodge specific, singular predators, not statistical clouds of predators occupying several bushes simultaneously. And yet, this smeared, probabilistic, undecided version of reality is not some exotic exception confined to laboratories and silver atoms. It is, according to every experiment we've ever run, simply how the universe actually behaves at its smallest scales. All the time, everywhere, including inside your own body, inside the atoms making up the chair you're sitting on, inside the very neurons currently allowing you to consider this idea in the first place. The only reason the world of chairs and coffee cups looks solid and definite is that trillions upon trillions of these superpositions are constantly colliding, interacting, and settling into agreement with each other, faster than you could ever notice the blur underneath. Which raises an obvious, slightly vertiginous question. If a single electron can exist in two places at once, and a single silver atom can spin both up and down simultaneously, what happens when you connect two of these particles together so intimately that whatever happens to one instantly seems to affect the other, no matter how far apart they travel? What happens when superposition isn't just about one particle being everything at once, but about two particles sharing a single unified fate across any distance imaginable? That, patient listener, is where entanglement begins. There is a cat in a box, and depending on who you ask, that cat is either alive, dead, or, most disturbingly, both at once. This thought experiment is possibly the most famous idea in all of quantum physics, and the strange part is that its creator invented it not to explain quantum mechanics, but to mock it. Let's set the scene properly. Inside a sealed box, entirely cut off from the outside world, sits a cat, a small amount of radioactive material, a Geiger counter, a hammer, and a vial of poison, the radioactive material has a precise 50% chance of decaying within a given hour. If an atom decays, the Geiger counter detects it, triggers the hammer shatters the vial, the poison releases, and the cat dies. If no atom decays, nothing happens, and the cat continues on with its day, entirely unaware it was ever in danger. Simple enough so far. This sounds like ordinary probability, the same kind you'd use to describe a coin flip or a dice roll. But here's where Erwin Schrödinger, the physicist who dreamed up this scenario, twisted the knife. According to the strict logic of quantum mechanics, that radioactive atom, before anyone checks on it, exists in superposition. It is not secretly decayed, waiting to be discovered. It is not secretly intact, waiting to be discovered either. It exists, genuinely, in both states simultaneously, a blur of decayed and not decayed, exactly like the electron sliding through both slits in our earlier chapter. And here's the disturbing consequence. If the atom is entangled with the Geiger counter, which is entangled with the hammer, which is entangled with the poison, which is entangled with the cat, then that superposition doesn't stay contained inside the atom. It spreads. Like ink dropped in water, it seeps outward through the entire chain of cause and effect, until, according to the strictest reading of the mathematics, the cat itself becomes caught in superposition, not resting peacefully in one state or the other, genuinely, simultaneously, both alive and dead, right up until someone opens the box and looks. Schrödinger did not propose this because he believed it. Quite the opposite. He found the idea so obviously ridiculous that he offered it as a kind of reductio ad absurdum, a way of holding up quantum theory's logic and saying, look how silly this becomes once you scale it up to something as large and familiar as a cat. And yet, nearly a century later, physicists are still arguing about exactly why he was wrong, or whether, in some deeply uncomfortable sense, he wasn't wrong at all. This is what's known, rather modestly, as the measurement problem, and it might be the single most unresolved question at the heart of modern physics. What, precisely, counts as an observation? Does the Geiger counter itself count as an observer, simply by detecting the decay? If a machine with no consciousness whatsoever can collapse a superposition just by interacting with it, then why would you need a cat, or a human, or anyone with actual awareness involved at all? And if the Geiger counter's detection is enough, then didn't the collapse already happen the moment the counter clicked, long before anyone ever opened the box? In which case, was the cat ever really in superposition in the first place, even for an instant? For decades, some physicists flirted with an almost mystical answer. Perhaps consciousness itself is special. Perhaps it takes an actual mind, a genuine act of awareness, to collapse a wave function, and everything else, cats included, remains stuck in quantum limbo until a sufficiently self-aware creature glances inside. This idea has a certain dramatic appeal. It also happens to be almost impossible to test, define, or take seriously as science, since nobody has ever managed to specify exactly how much consciousness is required, or whether a goldfish counts, or an insect, or a sufficiently philosophical thermostat. The far more satisfying, and far better supported, answer arrived under a different name entirely: decoherence. Here's the core insight, and it's worth taking slowly, because it dissolves the mysticism almost completely. Superposition isn't destroyed by consciousness peering into a box. It's destroyed by information leaking out. Think about what a sealed box actually is. It is never, in any real physical sense, perfectly sealed. Heat escapes through the walls. Air molecules inside the box bounce against the cat, against the vial, against each other, constantly recording, in some tiny physical way, whether the cat is alive or dead. A living cat's warm breath is entirely different from a dead cat's stillness. That difference doesn't stay secret inside the box. It bleeds outward, into the air, into the walls, into the surrounding environment, spreading and multiplying, faster and more thoroughly than you could possibly track. Once that information has spread widely enough, into billions of air molecules, into the very structure of the box itself, the superposition doesn't collapse because a philosopher finally opened the lid. It collapses because it has already become physically impossible to maintain. The two possibilities, alive and dead, have already become entangled with the entire surrounding universe. and trying to keep them both in play at that point would require somehow unmixing a cup of coffee back into separate streams of cream and espresso. Technically not forbidden by any law, but so staggeringly improbable that it never happens in practice. Here's an analogy worth sitting with, because it captures this shift precisely. Imagine a secret, whispered between two people inside a room with perfectly soundproofed walls. As long as that secret remains sealed inside, it exists in a strange kind of limbo. Nobody outside the room knows it. In some meaningful sense, out there in the hallway, the secret could still be anything at all. But now imagine someone cracks open the door, even slightly. Sound leaks out. Air currents shift and carry faint vibrations down the hallway. A draft slips under a neighboring door. The secret doesn't need a person to consciously overhear it and declare, "Aha, now I know." The moment information starts leaking into the surrounding environment, thoroughly and irreversibly, the secret has effectively already stopped being contained, whether or not any particular mind has consciously registered it yet. This is precisely what happens with Schrödinger's cat, and with quantum systems generally. The box was never truly soundproof, physically speaking. Heat, air, vibrations, they're always leaking. The superposition doesn't survive contact with all of that leaking information. It doesn't need a human eye at the end of the process to finish the job. The environment itself, cold and indifferent and utterly unconscious, is already doing the measuring continuously. Everywhere. All the time. And this reframes the entire question of where the quantum world ends and the ordinary classical world of cats and coffee cups begins. For a long time, people imagined this as a wall, a sharp dividing line, with tiny quantum weirdness on one side and normal, solid reality on the other. Decoherence tells a different story. There is no wall. There's only a gradient, a slope, a matter of speed. A single, carefully isolated electron, kept away from stray heat, light, and vibration, can maintain its superposition for a relatively long time, because almost nothing is leaking its information away. A cat, by grim contrast, is an enormous, warm, breathing, furry object, constantly shedding heat, jostling air molecules, radiating information into its surroundings from every direction, every fraction of a second. Its superposition, if it briefly existed at all, would decohere into a single definite outcome almost instantaneously, faster than any observer, conscious or otherwise, could possibly intervene. Not because a rule says cats can't be paradoxical. Simply because cats are far too busy leaking information into the universe to hold on to quantum ambiguity for any meaningful length of time. So the honest answer to when does the wave function collapse turns out to be considerably less mystical and considerably more mechanical than a century of philosophical hand-wringing suggested. It isn't waiting for a conscious mind to peer through a keyhole. It's a question of entanglement spreading outward, relentlessly, into an environment that never stops watching, in the most literal and unglamorous physical sense of that word. Schrödinger's cat, then, was never really trapped in some eerie balance between life and death, patiently waiting for a philosopher to open the lid and decide its fate. Long before that lid ever creaks open, the box itself, its warm air, its rattling walls, its leaking heat, has already asked the question, and reality has already answered. There is a blur woven into the fabric of reality itself. And no matter how good your equipment gets, no matter how clever your instruments become, that blur never goes away. This isn't a flaw waiting to be fixed. It's a fundamental law, and it goes by the name of the uncertainty principle. Let's state it plainly first, the way Werner Heisenberg himself arrived at it back in the 1920s. The more precisely you know a particle's position, the less precisely you can possibly know its momentum, which is, roughly speaking, how fast it's moving and in which direction. And the relationship runs both ways. Pin down the momentum with great precision, and the position dissolves into a haze. You simply cannot have both sharp and clear at the same time. Not because you're clumsy, not because your tools are cheap, because the universe itself refuses the request. This is the point where most people's intuition quietly rebels, so let's slow down and take it apart carefully. Surely, you might think, a particle just has a position and a speed, sitting there quietly, waiting for us to measure them. Surely our measuring devices are simply too crude to catch both at once, and one day, with better engineering, we'll manage it. This is an entirely reasonable guess. It is also, according to a century of experimental confirmation, completely wrong. Here is the deeper truth. A particle with a perfectly well-defined position isn't secretly hiding a single definite momentum that we're too clumsy to detect. It genuinely doesn't have one. Instead, it exists as a superposition of countless different momenta, all overlapping, all blurred together. And a particle with a perfectly well-defined momentum works the same way in reverse. It doesn't have one hidden, exact location. It's smeared out across a wide range of positions, all simultaneously real, the way we explored back in our chapter on superposition. Position and momentum aren't two independent facts about a particle that we're failing to read at the same time. They're mathematically, fundamentally incompatible with each other, like two ends of a seesaw. Push one side down, sharpen it, and the other side inevitably rises, blurring further. Let's reach for an image because this idea benefits enormously from something concrete. Picture a hummingbird hovering in your garden, wings beating so fast they nearly vanish into a shimmer. You want a photograph. So you set your camera to a lightning-fast shutter speed, and you get exactly what you wanted. A beautifully crisp, frozen image, every feather sharp, every wingtip perfectly defined. You now know, with wonderful precision, exactly where those wings were at that instant. But notice what you've lost. That fast shutter let in only the barest sliver of light, catching a single frozen sliver of time. From that image alone, you have no idea how fast the wings were beating, or in which direction they were moving. The motion, the momentum of those wings has vanished from your photograph entirely. So you try the opposite approach. You slow the shutter down, letting light pour in over a longer stretch of time. Now your photograph beautifully captures the sweep and blur of the wings in motion, revealing their speed and direction with real clarity. But that same long exposure has smeared away the bird's exact position. You can no longer say precisely where the wings were at any given instant. They're spread across the frame, ghostly, wherever the motion carried them. Sharpen the position, and the momentum blurs. Sharpen the momentum, and the position blurs. This is a wonderfully intuitive way to feel the shape of the uncertainty principle. But here's exactly where the analogy has to be handled with care, because it hides a trap. With the hummingbird, we know, without any doubt, that the real bird, at any given instant, did have one exact position and was moving at one exact speed. Our camera simply wasn't good enough to capture both at once. If you built an impossibly perfect camera, faster than any shutter ever engineered, capable of freezing an instant of time with zero blur while somehow still gathering enough light to also track motion, you could, in principle, capture both properties perfectly. The bird's blur was always a limitation of the camera, never a limitation of the bird. A quantum particle offers no such comfort. There is no theoretically perfect camera, no magical future measuring device, however cleverly engineered, that could ever capture both a particle's exact position and its exact momentum simultaneously. This isn't a technological gap waiting to be closed by better engineering, the way early telescopes eventually gave way to sharper ones. The uncertainty principle is not about disturbance caused by clumsy measurement, bumping into a delicate particle and knocking it off course. Even with an entirely hypothetical, perfect, non-disturbing measuring device, one that touches nothing and disrupts nothing, the uncertainty would remain, baked directly into the mathematics describing what a particle actually is. The unsettling truth, then, is stranger than any camera limitation. The hummingbird's position and momentum both genuinely exist at all times, whether you're watching or not, entirely independent of your equipment. But the electron's position and momentum do not both genuinely exist with perfect precision at the same time, camera or no camera, observer or no observer. Reality itself at that scale is slightly out of focus permanently by its own design. It isn't that we can't bring the picture into focus. It's that there is no perfectly focused picture waiting to be found. There's a wonderfully ironic historical footnote worth pausing on here. When Heisenberg first proposed this idea, many physicists, understandably uncomfortable, tried to rescue the situation by imagining some clever future experiment, some ingenious trick that might sneak around the limitation and measure both properties precisely. After all, physicists spent years, quite earnestly, designing elaborate thought experiments specifically intended to break Heisenberg's principle, the scientific equivalent of trying to find a loophole in a law of nature. Every single attempt failed in increasingly instructive ways, and each failure only strengthened the case that the uncertainty wasn't a temporary embarrassment. It was permanent. Nature, it turns out, checked everyone's homework and marked it wrong repeatedly, for decades. It's worth pointing out just how enormous the implications of this blur really are. Even though at human scale, we never notice it at all. The uncertainty principle technically applies to everything, including you, including the chair you might be sitting in, including a thrown baseball. But the effect is so vanishingly, almost comically small at the scale of everyday objects that it never registers. A baseball's position and momentum are, for all practical purposes, both perfectly knowable, because the built-in blur is smaller than anything any instrument or any human sense could ever detect. It's only when you shrink down to the scale of electrons and atoms that this blur stops being a theoretical footnote and becomes the dominant, unavoidable feature of reality. And this blur isn't merely a curiosity confined to abstract particles bouncing around in laboratory experiments. It has real physical consequences that shape the universe you live in. It's part of the reason atoms don't collapse in on themselves, the reason electrons maintain their strange cloud-like orbits around nuclei, rather than spiraling inward to a single point. If a particle's position and momentum could both be pinned down with perfect precision, an electron could simply sit still, motionless, directly on top of the nucleus. But the uncertainty principle forbids this outright. Confine a particle's position too tightly, and its momentum is forced to blur wildly in response, giving it an irreducible, restless energy that keeps it in perpetual motion, no matter how cold or still the surrounding universe becomes. In a very real sense, this built-in blur is part of what keeps matter from collapsing into nothingness. The universe's fuzziness isn't a bug. It's structural. It's load-bearing. So the next time you glance at something solid, something perfectly still, a coffee cup, a stone, a sleeping cat, remember that underneath that stillness, at the scale where electrons live, nothing is ever quite that still. And nothing is ever quite that precise. Reality, at its foundation, isn't a sharp photograph. It's closer to that long exposure of the hummingbird's wings, a soft, permanent, irreducible blur. And the strange part is that blur isn't hiding a sharper picture underneath. The blur is the picture. Albert Einstein spent the final decades of his life trying and failing to prove that quantum mechanics was wrong. Not because he misunderstood it, because he understood it perfectly and found what it implied so deeply unacceptable that he devoted his enormous intellect to hunting for the flaw. He never found it. Instead, he stumbled onto something even stranger, a phenomenon he himself named, with unmistakable disdain, spooky action at a distance. Today we call it entanglement. In 1935, Einstein, along with two colleagues, Boris Podolsky and Nathan Rosen, published a thought experiment now known simply as the EPR paradox, built entirely to expose what they saw as a fatal flaw in quantum theory. Here was their argument, and it's worth following closely, because it's beautifully logical, even though, as it turns out, it was wrong. Imagine you create a pair of particles together in a way that links their properties. Perhaps their combined spin must always add up to zero, meaning if one is measured spinning up, the other must be spinning down, guaranteed. Now separate these two particles, sending one to a laboratory on one side of the galaxy, and the other to a laboratory on the opposite side. According to quantum mechanics before measurement, each particle exists in superposition, neither definitely up nor down, exactly as we explored a few chapters back. But the instant someone measures the first particle and finds it spinning up, the second particle, however impossibly distant, must instantly be spinning down. Not eventually. Not after some delay while information travels between them. Instantly. To Einstein, this was absurd. Nothing, according to his own theory of relativity, can travel faster than light. No signal, no influence, no information. So how could measuring one particle here instantaneously affect a particle on the other side of the galaxy? Einstein's proposed solution was elegant, cautious, and crucially, testable. He argued that the particles must have carried hidden instructions all along, decided the moment they were created, long before anyone measured anything. The second particle wasn't being instantly influenced by the first. It had simply always been spinned down quietly, secretly, from the very beginning, exactly like two gloves packed into separate suitcases, one left-handed, one right-handed, decided the moment they were packed, discovered only later. Quantum mechanics, Einstein argued, wasn't wrong exactly. It was simply incomplete, missing some deeper layer of hidden variables that would restore good old-fashioned common sense to the universe. For nearly 30 years, this remained an elegant philosophical standoff. seemingly impossible to settle experimentally. Then, in 1964, a physicist named John Bell did something remarkable. He found a way to actually test it. Bell's insight, now known as Bell's theorem, was a piece of mathematics rather than a philosophical argument, and that made all the difference. He showed that if Einstein were correct, if these particles really did carry predetermined hidden instructions decided in advance, then certain statistical correlations between measurements, taken across many repeated trials, would be mathematically bounded. There would be a hard ceiling on how strongly correlated the results could possibly be, a limit no hidden variable theory could ever exceed. But quantum mechanics predicted something different. It predicted correlations that would exceed that ceiling. Not infinitely, not dramatically, but measurably, precisely, and unmistakably. This turned a philosophical argument that had lasted 3 decades into a question any sufficiently careful experimentalist could actually answer. And through the 1970s, 80s, and beyond, physicists including John Clauser, Alain Aspect, and later Anton Zeilinger built increasingly rigorous versions of this experiment. Entangled particles sent flying apart, measured independently, statistics compared afterward. Every single time, across decades of refinement, closing every conceivable loophole, the results violated Bell's ceiling, exactly as quantum mechanics predicted, and exactly as Einstein's hidden variables forbade. This body of work eventually earned Clauser, Aspect, and Zeilinger the Nobel Prize in Physics in 2022, nearly 6 decades after Bell's original insight. Einstein was wrong. Not sloppy, not confused, just wrong, in the most interesting possible way. The particles were never carrying secret, pre-written instructions. The correlation between them is real, instantaneous, and genuinely inexplicable by anything resembling ordinary, local, common-sense physics. Let's find our footing with an analogy, because entanglement, more than almost anything else in this story, resists intuition unless you build the right picture. Imagine writing 2 halves of a single poem, tearing the page cleanly down the middle, sealing each half into its own envelope, and mailing one to a friend on the moon and the other to a different friend on Mars. Months later, your friend on the moon opens their envelope and reads the first half of a poem about rain. They instantly know with total certainty that their counterpart on Mars is holding the matching second half, also about rain. This is unremarkable. It's ordinary correlation. The poem was written in advance, torn in two, and simply discovered later. No mystery here, just distance and a delayed reveal. Quantum entanglement asks you to imagine something considerably stranger. Picture those same 2 envelopes, mailed to the moon and to Mars, except this time, neither envelope actually contains a finished poem at all. They contain something closer to pure potential, blank pages humming with every possible poem they might become. Then, at some specific moment, your friend on the moon opens their envelope, and a poem about rain instantly appears on the page, as if written into existence by the act of opening it. And at that exact same instant, with no time for any signal to travel anywhere, the envelope on Mars fills in too, completing the matching second half, also about rain. The poems weren't hidden inside the envelopes the whole time, waiting patiently to be discovered, the way Einstein hoped. And no message traveled between the moon and Mars, carrying instructions. 2 halves simply co-arose, together in the same instant, correlated perfectly, despite there being no possible channel of communication fast enough, or perhaps existing at all, to coordinate them. This is, understandably, the point where people start asking the obvious follow-up question. If measuring one particle instantly determines the state of the other, across any distance, doesn't that let you send a message faster than light? Could you use this to, say, transmit information to Mars instantaneously, breaking one of the most sacred rules in all of physics? The honest, slightly disappointing answer is no. And the reason why is elegant. You cannot choose the outcome of your own measurement. When you open your envelope on the moon, you don't get to decide whether it reveals rain or sunshine. Quantum mechanics only tells you the probabilities. You measure, and the universe hands you a result, spin up or spin down, entirely at random, with no control on your end whatsoever. Since you can't control what you get, you can't encode any deliberate message into it. Your friend on Mars opening their envelope receives a result that perfectly correlates with yours, but neither of you chose what that result would be. There's no message, just a shared, unplanned coincidence, arriving simultaneously across any distance you like. So entanglement doesn't violate relativity by smuggling information faster than light. What it violates is something arguably even more sacred, something physicists call local realism. Local realism is the perfectly reasonable, deeply intuitive assumption that objects have definite properties independent of measurement, and that nothing can influence anything else faster than light can travel between them. Bell's theorem, backed by decades of increasingly airtight experiments, proved that the universe simply does not respect this assumption. Reality is, in some fundamental sense, non-local. Correlations exist between distant particles that no amount of local, hidden, prearranged instruction could ever produce. This is perhaps the strangest destination our journey has reached so far. Stranger even than particles occupying two places at once. Stranger than cats caught in metaphorical limbo. It suggests that the universe, at its deepest level, isn't built entirely out of separate, independent pieces quietly minding their own business, exchanging signals only when convenient. Some correlations, entangled correlations, simply exist across the fabric of reality itself, correlated not because anything passed between them, but because, in some sense too strange for ordinary language, they were never truly separate to begin with. Throw a ball at a wall, and if that ball doesn't have enough energy to climb over it, it bounces back. Every single time. No exceptions. This is one of the most reliable facts in classical physics, and quantum mechanics breaks it completely, in a way that quietly powers the very sun keeping you alive. This phenomenon is called quantum tunneling, and it describes something that, by every rule of ordinary common sense, should simply never happen. A particle passes straight through a barrier. It does not have enough energy to cross. Not around it. Not over it. Through it. As if the wall weren't fully there. To understand why this is so strange, let's linger on the classical picture first, because it's worth appreciating just how absolute it is. Roll a ball up a hill, and if it doesn't have quite enough speed to reach the top, it will slow, stop, and roll back down, every time, without fail. There is no version of ordinary physics in which that ball occasionally, mysteriously, appears on the other side of the hill without ever having gone over it. Energy is energy. A barrier is a barrier. If you don't have enough of the former, you don't get past the latter. This has been true for every thrown rock, every parked car, every dropped enemy fortress in the history of human warfare. Quantum particles were apparently never told about this rule. Remember, from a few chapters back, that a quantum particle isn't a tiny solid marble sitting at one exact point. It's described by a wave function, a spread of probability extending through space, telling you everywhere the particle might possibly be found. Here is the crucial detail. When that wave function encounters a barrier, an energy wall, the particle classically shouldn't be able to cross. It doesn't hit that wall and simply stop, the way a solid ball would. Instead, the wave function decays. It shrinks exponentially as it pushes into the barrier, growing fainter and fainter the deeper it goes. But it never actually reaches zero. And if the barrier is thin enough, that faint decaying wave function emerges on the other side, still very small, but very much still there. And wherever the wave function is non-zero, there is a real physical chance of finding the particle, which means every so often, seemingly against every rule of energy and common sense, the particle simply appears on the other side of a wall it never had the energy to climb. This isn't a rare theoretical curiosity confined to physics classrooms. It happens constantly, all around you, and without it, you wouldn't exist to hear about it. Consider the sun. Stars generate their staggering output of energy by fusing hydrogen nuclei together, protons crashing into protons. But protons are positively charged, and like charges repel each other fiercely. Classically, two protons approaching each other should simply bounce apart, repelled long before they ever get close enough to fuse. According to the raw energies involved inside the sun's core, fusion, by classical physics alone, shouldn't be happening at anywhere near the rate it actually does. And yet it happens reliably, continuously, for billions of years, because protons occasionally tunnel straight through that electromagnetic wall of repulsion, slipping past a barrier they never had enough energy to overcome. Without tunneling, stars would burn far more slowly, or perhaps not ignite through fusion at all. The sun on your skin right now is, quite literally, sunlight generated by billions of quantum impossibilities happening every single second. Tunneling also explains radioactive decay. Inside certain unstable atomic nuclei, alpha particles are held in place by forces that, classically, should keep them permanently trapped, the nuclear equivalent of a maximum security wall. And yet, given enough time, they occasionally tunnel straight out, escaping a prison that should have held them forever. This is precisely why radioactive decay is probabilistic rather than scheduled. Why we describe it in terms of half-lives rather than exact countdown clocks. Each nucleus is, in effect, quietly testing the wall, moment by moment, for a way through that shouldn't exist, and eventually, unpredictably, finding one. And in a rather elegant twist, humans have learned to harness this same effect deliberately. The scanning tunneling microscope, one of the most important inventions in modern nanotechnology, works by exploiting exactly this phenomenon, detecting the faint trickle of electrons tunneling between a microscopic tip and a surface, close enough to measure the position of individual atoms one at a time. We didn't just discover this quantum leak. We built an instrument specifically designed to listen to it. It's worth being precise about how rare any single tunneling event actually is, because tunneling is not a loophole that particles casually stroll through whenever convenient. Overwhelmingly likely, in any single encounter with a barrier, that a particle simply reflects, bouncing back exactly as classical physics would predict. Tunneling is a probability, often an extraordinarily small one. But extraordinarily small is not the same as zero. And when you're dealing with the unfathomable number of particles inside a star, or the patient span of geological time governing radioactive decay, even a tiny probability multiplied by enough attempts becomes a certainty. The sun doesn't rely on any single proton getting lucky. It relies on the sheer, staggering scale of attempts, trillions upon trillions of them, ensuring that occasionally happens constantly, somewhere, at every moment. Let's reach for an image to hold all this together, because tunneling, more than almost any idea so far, rewards a concrete picture. Imagine standing on one side of a tall fence, wrapped in thick fog. You don't have the strength to climb it. Classically, that's the end of the story. You're stuck, and you'll remain stuck, no matter how many times you try, because trying harder doesn't change how much energy you have. But in the quantum picture, you were never a single solid person standing at a single solid point. You are in truth a hazy cloud, spread thinly through space, most of you concentrated on your side of the fence, but not all of you. A faint, whisper-thin wisp of that cloud extends outward, through the fence itself, thinning almost to nothing, but never quite vanishing entirely, reaching the other side. And every so often, unpredictably, rarely, without warning or ceremony, you find yourself standing over there. You didn't climb the fence. You didn't break it. You leaked through it because some faint trace of you was, in a very real sense, already on both sides the whole time. The fence didn't fail. Your solidity did. This is the deepest lesson tucked inside quantum tunneling. In this universe, nothing is ever perfectly, absolutely contained. Every impossible barrier is really just a place where probability grows extremely thin, stretched almost to nothing, but never quite reaching zero. And given enough time, enough attempts, enough patient trillions of tries, even the thinnest possibility eventually becomes an event, powering stars, dating fossils, and letting curious humans photograph atoms one at a time. There is no such thing as empty space. Not really. Not anywhere. Not ever. And this final upgrade to our picture of reality is perhaps the strangest one yet, because it asks you to stop thinking of particles as tiny objects at all, and start thinking of them as something closer to ripples. Everything we've covered so far, the electrons, the photons, the silver atoms, has been described the way physics traditionally likes to describe things, as particles. Small, discrete, countable objects. But by the middle of the 20th century, physicists building on quantum mechanics arrived at a deeper, stranger framework called quantum field theory, and it quietly replaced the particle with something far more fundamental. Here is the core idea. The universe, according to this framework, is not fundamentally made of particles at all. It's made of fields. Invisible, intangible fields, stretched out across the entirety of space, filling every corner of the cosmos, whether or not anything is happening in that corner at all. There is an electron field permeating all of existence. There is a photon field, a quark field, and a particle in this deeper picture is not a tiny ball traveling through the field. A particle is a ripple in the field, a localized disturbance, a vibration, a little knot of excitation moving through something vast and invisible that was already there. This has a beautiful, almost poetic consequence. Every single electron in the universe, the ones in your own body right now, the ones in a distant star, the ones inside a calculator on the far side of the galaxy, are not separate little objects that happen to resemble each other. They are ripples in the exact same underlying electron field, the one field that spans the entire universe. Every electron that has ever existed or ever will exist is, in some sense, the same field, just disturbed in slightly different places. This is why every electron in the universe is utterly, perfectly identical, indistinguishable, in every measurable way. They're not manufactured copies of some template. They're the same fabric, rippling. Now here comes the truly unsettling part, and it follows directly from an idea we already met a few chapters back. The uncertainty principle. Remember, the uncertainty principle tells us that certain pairs of properties, like position and momentum, can never both be perfectly defined at once. It turns out a similar relationship exists between energy and time. And this has a consequence that should, by all rights, feel impossible. It means these underlying fields can never be perfectly, absolutely still. Not even in a perfect vacuum. Not even in a region of space with no particles, no light, no matter, nothing at all, stripped down to the most literal definition of emptiness anyone could construct. Because if a field were ever truly perfectly flat and motionless, that would mean its energy was perfectly, precisely zero for an indefinite length of time. And the uncertainty principle simply forbids that kind of precision. So the fields tremble, constantly, everywhere. Even in the emptiest possible patch of space you could imagine, these fields are quietly, ceaselessly fluctuating, jittering with a restless energy that can never be fully switched off. And these fluctuations do something extraordinary. Every so often, a fluctuation in the field becomes large enough, briefly, to produce something that looks exactly like a real particle. Except it comes paired with its opposite, a particle and its corresponding antiparticle, flickering into existence together out of pure, restless nothing, for an unimaginably brief instant, before rushing back together and annihilating, vanishing as quickly as they appeared. Physicists call these virtual particles, and the phrase is fitting. They're not stable. They're not directly observable, sitting still long enough to photograph. But their fleeting, borrowed existence is entirely real, and it leaves fingerprints on the world that we can actually measure. Two of these fingerprints deserve special mention, because they turn this idea from strange philosophy into confirmed laboratory fact. The first is called the Casimir effect. Take two ordinary metal plates, place them extremely close together in a vacuum, closer than a hair's width, and something bizarre happens. The plates are gently pushed together, drawn inward, as if some invisible hand were squeezing them. There's no material force, no glue, no wire pulling them. The explanation lies entirely in the restless vacuum. Outside the plates, in the wider open space, the field can fluctuate freely, producing its full restless spectrum of virtual particles. But squeezed into the narrow gap between the plates, only certain wavelengths of fluctuation actually fit, the way only certain notes fit inside a short organ pipe. This slight imbalance, more restless fluctuation pushing in from outside than can exist in the cramped space between, creates a measurable net force, gently squeezing the plates together. Physicists have measured this force directly, and it matches the predictions with remarkable precision. The second fingerprint is called the Lamb shift, a tiny, precisely measurable shift in the light spectrum given off by hydrogen atoms, a shift that simply shouldn't exist according to earlier, simpler versions of quantum theory. It turns out this shift arises because the electron inside a hydrogen atom is constantly, imperceptibly jostled by the restless sea of virtual particles, flickering in and out of the surrounding vacuum. The electron isn't orbiting through calm, empty space. It's orbiting through a churning, restless field, and that churning leaves a subtle, permanent mark on the atom's behavior, one delicate and precise enough to be measured in laboratories decades ago, confirming the restless vacuum wasn't merely a mathematical convenience. All of this comes together in a theory called quantum electrodynamics, often abbreviated QD, which describes precisely how light and matter interact using this entire field-based picture. QED holds the extraordinary distinction of being, by most measures, the most precisely tested theory in the entire history of science. It predicts a specific property of the electron, called its magnetic moment, to an accuracy of roughly 12 decimal places, agreeing with direct experimental measurement to a level of precision almost impossible, To convey in ordinary language, if you measured the distance from New York to Los Angeles with that same relative precision, you'd be accurate to within the width of a single human hair. Nothing else humans have ever built, tested, or theorized comes remotely close to that level of confirmed accuracy. Let's close this chapter with an image, because it captures, better than any equation could, what this restless vacuum actually feels like. Picture a vast ocean at night, viewed from a distant shore. From that distance, in the darkness, the water looks utterly flat, still, silent, empty. But move closer and closer still, until you're hovering just above the surface itself. And that flatness dissolves entirely. The water is never actually still. Tiny ripples rise and fall constantly, swells appear and vanish, even on a night with no wind and no passing boat to explain them. The stillness was always an illusion created by distance, blurring away a surface that never once stopped moving. Now imagine, every so often, one of those tiny ripples rises just high enough to briefly separate from the surface entirely, forming a small distinct droplet, hovering for the briefest possible instant above the water, before falling back and disappearing, folding back into the restless ocean it came from. That fleeting droplet is a virtual particle. The ocean itself, endlessly rippling, endlessly restless, is the quantum field, stretched across the whole of space, incapable of ever truly going still. Empty space, then, was never actually empty. It was always this ocean churning quietly beneath the appearance of calm, and everything solid, every atom, every star, every one of us, floats and forms atop a vacuum that has never, for even an instant, stopped moving. After everything we've covered, the electrons in two places at once, the cat's caught in limbo, the correlation spanning any distance, the vacuum that never sleeps, you might reasonably expect that physics, by now, has settled on what it all actually means. It hasn't. And this is perhaps the strangest fact in this entire strange story. The mathematics of quantum mechanics is, by any measure, a spectacular success. It predicts experimental results with a precision bordering on the absurd, as we saw with QE's 12 decimal places. Every physicist agrees on the equations. Every physicist agrees on the numbers those equations produce. And yet, ask a room full of physicists what those equations actually mean. What is genuinely happening out there in reality? When a wave function does whatever it does, and you will get answers so different from each other that they barely sound like they're discussing the same universe. Let's walk through the major camps in this century-long disagreement, because each one accepts the exact same math, the exact same experimental results, and tells an entirely different story about what's underneath. The oldest, and for decades, the most dominant view is called the Copenhagen interpretation, developed largely by Niels Bohr and Werner Heisenberg, the same figures who helped build quantum theory in the first place. Copenhagen takes a position that is, in its own way, almost defiantly modest. It says the wave function isn't a description of some real physical object quietly existing out there in the world. It's simply a tool, a mathematical device for calculating the probability of different outcomes. According to this view, it's not merely difficult to ask what a particle is really doing before measurement. It's meaningless. The question itself doesn't apply. Reality, in any sense we can meaningfully discuss, only comes into being at the moment of measurement. Before that, Copenhagen politely declines to speculate. For many physicists, this was always deeply unsatisfying. A little like being told the map is all there is, and asking about the actual territory is simply against the rules. So other interpretations emerged, each trying to restore some deeper sense of what's really going on. In 1957, a graduate student named Hugh Everett proposed something audacious, now known as the many worlds interpretation. Everett's central claim was startlingly simple once you say it out loud. What if the wave function never actually collapses at all? What if, instead, every possible outcome genuinely happens, each one unfolding in its own separate, complete branch of reality? Under this view, when you measure an electron and see it spinning up, you haven't caused some mysterious collapse of possibility into a single outcome. You've simply found yourself in the branch of reality where it came up spinning up. Somewhere else, in an equally real, equally physical branch that you will never again have contact with. Another version of you, just as convinced of their own singular reality, is looking at a detector reading spin down. The universe, in this picture, isn't collapsing anything. It's constantly silently splitting into more branches than could possibly be counted, every single time any quantum event occurs anywhere. A third path, developed originally by Louis de Broglie and later revived and extended by David Bohm, takes a very different route entirely, sometimes called pilot wave theory or Bohmian mechanics. This interpretation makes a rather comforting claim. Particles, it insists, do have definite real positions at all times, exactly the intuition classical physics always assumed. There's no fuzziness, no genuine indeterminacy hiding at the core of things. Instead, each particle is guided along its path by an invisible companion, a pilot wave, that steers it precisely, deterministically, moment to moment. The catch, and it's a significant one, is that this pilot wave has to act non-locally, instantly connected across any distance in order to reproduce entanglement correctly. So Bohmian mechanics restores comforting determinism, real particles with real positions, at the cost of embracing exactly the kind of spooky, non-local connection Einstein found so troubling. And then there's a considerably more recent and unusual perspective called cubism, short for quantum Bayesianism. Cubism takes the boldest step of all, suggesting the wave function was never a description of the world at all, not even a calculating tool for objective probabilities. Instead, it represents your personal degree of belief, a statement about what you, specifically, expect to observe, given everything you currently know. Under this view, quantum mechanics was never really a theory about particles and fields out there in an external world. It's a theory about the relationship between an observer and their own expectations. Two different observers, with different information, might reasonably assign entirely different wave functions to the exact same physical situation, and cubism insists neither of them is wrong. Here is the remarkable fact tying all of this together, the one that makes this chapter so different from everything before it. After more than a century of debate, involving some of the sharpest minds in the history of science, nobody has ever devised an experiment capable of distinguishing between these interpretations. Not one. Every single one of them, Copenhagen, many worlds, Bohmian mechanics, cubism, and several others we haven't even mentioned, predicts precisely the same experimental outcomes, every single time, down to those same staggering 12 decimal places. They are, in the strictest experimental sense, indistinguishable. The disagreement isn't about what will happen in any laboratory. It's entirely about what is actually happening underneath, in whatever sense that phrase can even be said to mean anything. This brings us to an image worth sitting with because it captures the peculiar position physics finds itself in today. Imagine a room full of people, standing together in front of the same abstract painting. They agree completely on the canvas itself. Every color, every brushstroke, every measurable physical detail. There is no dispute whatsoever about what's actually on the wall. And yet, ask them what the painting means, what it's actually depicting, and the room erupts into total disagreement. One insists it's clearly a forest, dense and tangled. Another sees, unmistakably, a portrait of a mind, thoughts folding over each other. A third describes an intricate map, charting countless branching worlds layered impossibly on top of one another. Earth, quietly, suggests it isn't a picture of anything external at all. It's simply a mirror, reflecting each viewer's own expectations back at them. Every one of them is looking at precisely the same canvas. None of them disputes a single, measurable fact about it. And yet they leave the room having witnessed, in some sense, entirely different paintings. This is precisely where quantum mechanics stands today, nearly a century after Planck's reluctant quanta first cracked open the clockwork universe. The mathematics is not in question. The experiments are not ambiguous. Every prediction has been tested, retested, and confirmed to a precision that borders on the miraculous. But what any of it actually means, what is genuinely happening in the space between measurements, whether worlds are splitting, whether particles carry hidden positions, whether the whole question is simply the wrong one to ask, remains entirely, stubbornly open. Perhaps it always will. And there is something quietly beautiful in that unresolved ending. Physics, so often imagined as a discipline marching steadily toward final answers, has instead delivered one of its greatest achievements alongside one of its deepest, most honest confessions of uncertainty. The universe, at its foundation, works exactly as the equations describe. What that foundation actually is, underneath the numbers, remains a mystery every bit as strange and every bit as unresolved as the flickering vacuum, the entangled particles, and the cat that was never quite one thing or the other. We began this journey with certainty, dying quietly in a German physicist's office in 1900. We end it somewhere far stranger and far closer to home. Not in a laboratory, not in an equation, but here, inside you, right now as you listen. Let's start with a machine that shouldn't work, and yet, increasingly, does. The quantum computer. Every device you've ever used, every phone, every laptop, every calculator, processes information using bits, tiny switches that are always either off or on, a 0 or a 1, with absolutely nothing in between. This has been the foundation of computing since its invention, and it is by now a very well understood, very reliable idea. Quantum computing throws that foundation out entirely, replacing ordinary bits with something called qubits. Remember superposition from several chapters back. A qubit exploits exactly that principle. Instead of being locked into a definite 0 or a definite 1, a qubit can exist as a superposition of both simultaneously, right up until it's measured. Now, here's where it becomes genuinely powerful rather than merely strange. Link several qubits together using entanglement, and you create a system that can, in a sense, explore an enormous number of possible combinations all at once, rather than checking them one at a time, the way a classical computer must. Certain problems, ones that would take a classical computer longer than the age of the universe to solve by brute force, become, in principle, solvable in a reasonable amount of time. This is not easy to build, and the difficulty comes from an idea you've already met. Decoherence. A qubit's delicate superposition is destroyed the instant it interacts too much with its surrounding environment, heat, vibration, stray electromagnetic noise. Exactly like the cat's superposition collapsing the moment information leaked into the air around it. This is precisely why quantum computers require such extraordinary conditions. Chambers cooled to temperatures colder than deep space. Isolated as completely as engineering allows from any stray disturbance. Building a quantum computer is, in a very real sense, an ongoing battle against the universe's relentless tendency to measure everything, all the time, whether you want it to or not. Entanglement offers something else too, beyond raw computing power. It offers a genuinely new kind of security, called quantum cryptography. Here is the elegant trick. If you encode a secret key using entangled particles, any eavesdropper attempting to intercept and read that key has to measure the particles. And measurement, as we established firmly back in Chapter 2, disturbs a quantum system. The entanglement itself would visibly change, leaving an unmistakable fingerprint of interference. Unlike traditional encryption, where a sufficiently patient hacker might crack a code without anyone ever noticing, quantum cryptography makes eavesdropping detectable, in principle, every single time. It converts a law of physics into a burglar alarm. Now let's step somewhere genuinely surprising, a frontier still being actively explored called quantum biology. For a long time, quantum effects were assumed to matter only at extremely cold temperatures, or extremely tiny scales, far removed from the warm, messy, chaotic environment of living cells. Recent research suggests this assumption may have been too hasty. Consider the European robin and countless other migratory birds, which navigate vast distances with a precision that has puzzled biologists for generations. One leading theory suggests these birds may be sensing Earth's magnetic field using a mechanism inside their eyes involving entangled electron pairs, sometimes called the radical pair mechanism. Light striking a molecule in the bird's eye may briefly create two entangled electrons, and Earth's magnetic field subtly influences how that entanglement behaves, providing the bird with a kind of built-in quantum compass. It remains an active and somewhat contested area of research, but the evidence has grown compelling enough that few biologists dismiss it outright anymore. There's more. Photosynthesis, the process every green plant uses to convert sunlight into usable energy, appears to rely on something resembling quantum coherence. A delicate, wave-like spreading of energy across multiple pathways simultaneously, allowing plants to funnel captured sunlight toward the right destination with startling efficiency. And certain enzymes, the tiny biological machines driving chemical reactions inside your own cells, appear to speed up those reactions using quantum tunneling, the very phenomenon that powers stellar fusion, borrowed here for something considerably more modest. Digesting your lunch. None of this means birds or plants are somehow deliberately using quantum computers. It means the line we've comfortably drawn between the quantum world of tiny particles and the classical world of living, breathing organisms may be considerably blurrier than anyone assumed. a gradient rather than a wall, exactly as we discovered back in our chapter on decoherence. And yet, for all this progress, the deepest questions remain wide open, exactly where we left them. Quantum mechanics describes the very small with extraordinary precision. General relativity, Einstein's other great achievement, describes gravity and the very large with equally extraordinary precision. The trouble is, nobody has yet managed to combine these two theories into a single, consistent picture. Attempt to apply quantum rules directly to gravity, and the mathematics breaks down, producing nonsense infinities where sensible numbers should be. This unsolved puzzle, called quantum gravity, remains one of the largest unclaimed prizes in all of physics, pursued through approaches with names like string theory and loop quantum gravity, none of which have yet been confirmed by experiment. And the measurement problem, which we sat with carefully back in Chapter 4, remains every bit as unresolved today as it was when Schrödinger first imagined his unfortunate cat. Copenhagen, many worlds, Bohmian mechanics, cubism, all still standing, all still disagreeing, a century later, about what is actually happening beneath the surface of the math. Perhaps underneath quantum mechanics itself, there exists some deeper theory we haven't yet glimpsed, the way Newton's tidy clockwork universe eventually gave way to Planck's reluctant quanta. Perhaps quantum mechanics is not the final word, but simply the current word, the best approximation available until someone somewhere notices the next crack in the machine. Let's close then with the image this entire journey has been quietly building toward. Imagine spending an evening learning chess. The knight's peculiar L-shaped leap, the bishop's diagonal glide, the queen's commanding reach across the board. You learn the rules carefully, piece by piece, until the whole game finally makes sense. And then someone leans over and tells you something unsettling. Those wooden pieces you've been moving were carved from a tree, and that tree grew from a seed shaped at every stage by quantum processes, sunlight arriving in discrete packets, chemical bonds held together by the uncertainty principle, cellular machinery quietly tunneling its way through reactions too slow without it. The board itself is built from the same quantum stuff. And you, sitting there, turning these pieces over in your fingers, learning the rules, are doing so with a brain running on quantum mechanical chemistry. Every thought a cascade of electrons behaving exactly as strangely as everything we've discussed across this entire journey. The chess game was never separate from quantum physics. Understanding quantum mechanics doesn't just explain some obscure corner of reality, tucked away in laboratories and particle accelerators, far removed from ordinary life. It reveals that there was never anything else. No hidden classical world sitting comfortably underneath, waiting to be found. Just this, all the way down. The board, the pieces, and the player, all quantum, all the way through. Every atom in your body arrived by fusion inside a star that only ignited because protons tunneled through a wall they had no business crossing. Every photon of light striking your eyes right now travels as a wave and lands as a particle, precisely as strange as the electron passing through both slits at once. Every thought forming in your mind depends on chemical reactions unfolding at the mercy of an uncertainty that can never be fully resolved. The quantum world was never somewhere else, tucked away in laboratories, distant from ordinary experience. It was always here. It was always this. It was always you.